Hello everyone. So now we are going to continue with more ideas leading to the new quantum mechanics. We just finished going over the Bohr model and how that relates to spectroscopy. Now we're going to start with ideas that are going to be replacing the Bohr model. Now we're going to focus on this module with wave-particle duality, and then the next module will look at the uncertainty principle. But first, let's talk about wave-particle duality. Now, so it was thought that electrons were thought of as particles in the past. So in classic mechanics, electrons were particles, and they were known to have some mass. But they learned that they are shown to also have a wave-like nature. Okay. And electrons then can act as both a particle and a wave. So Einstein, he described that light had the particle and wave-like behavior. So I hope you guys recall that from a previous module. Einstein, with light, it had a wave-like and particle-like behavior. Okay, so wave-like, it could be described, the properties were wavelength frequency. The particle-like behavior, he described that individual quanta of light are called photons, so we learned about photons. But de Broglie in 1924 had the idea that matter, so for example, electrons, can have both particle-like and wave-like properties. Okay, so thus the wave-particle duality. Now this was explained through diffraction. So we learned about diffraction before, but here the expected behavior was that you have your matter, this time the electrons. They had the double slit experiment again, so electrons were going through the two slits, and they expected that they would see bright spots on both ends of the screen. But what actually happens is, again, here's our electron source. They're shooting these electrons, and they saw that they had an interference pattern. So they thought, okay, that's really strange. They didn't quite believe that electrons can behave as waves at the time. So they thought, well, maybe they're just shooting. When they shot the electrons, they're going every which way and are interfering with each other. So they decided to shoot one electron at a time. And when they did this, they did it over a very long period of time. So they tried their best to have one electron going through these slits one at a time for hours. And then what they found again was that they still saw an interference pattern. So to them, this really didn't make sense. This weirded them out. So what they thought then was, okay, let's observe. So I'm going to try to draw an eyeball. I don't know how to draw an eye. So there's an eye. Here's some lashes. So they tried to observe the electrons going through the hole. And they did this by flashing a light. And when those electrons are going to be released, when they incident with an electron, they should see which hole it goes through. And when they observed that, something even weirder happened. It went back to acting like a particle. So it went back to acting like a particle. So this actually gave them evidence at the time that, okay, there must be some type of wave-particle duality. So de Broglie combined Einstein's equation and the equation of the energy of a photon to derive the de Broglie relation. So here we know that lambda is the wavelength. We know h is Planck's constant. M is going to be the mass, and v is our velocity. Okay, so the energy of the photon here, okay, I don't know why I said energy of the photon, but please ignore I said that. All right, so let's look at an example of how we can use this. So now we can calculate a wavelength for an electron. So keep in mind again, they thought they were just particle-like. So by using this formula, so we have lambda equals h, and that's an h again, over mass over nu. So calculate de Broglie wavelength of an electron with a speed of 1 × 10⁶ meters per second. All right, so what are we given here? We know we are given our Planck's constant, which we know that value. But before we do that, how do we know the mass of an electron? Well, we would just have to look it up. It's something that is given. So our mass of our electron is 9.11 times 10⁻31, and that is going to be kilograms. Okay. Now let's go ahead and write our Planck's constant again. It's 6.626 times 10⁻34, and we know that was joules times a second. Okay. And we're also given the velocity. Now our velocity is 1 times 10⁶ meters per second. Now what should we notice about this formula already? Now we want the wavelength, so we need to get a meters out, right? So we have meters per second. Okay, that'll work out to give us our meters. But what about this joules? That joules is very useful, right? So you guys recall that the joule is equal to the kilogram times meter squared times second squared. Now we did that a lot, right? So I'm just going to plug this in for that unit. So now I'm just going to erase this so I don't have to write it over again. So if we go ahead and plug this in, that's 34. So we're going to plug in kilograms times meter squared times second squared. We know that this can cancel with that, and we're going to get kilogram times meter squared all divided by a second. So hopefully I did that quick, but hopefully you guys remember that from before. So I'm just going to erase this so we can see that unit. Okay, so there's the unit. So kilogram meter squared per second for our h. All right, so now let's plug everything into our formula. So Planck's constant then will be 6.626 times 10⁻34 kilogram meter squared divided by our second. So again, we're copying this formula. So there's Planck's constant in our numerator. Now what's in our denominator? The mass of the electron. So this guy has to be 9.11 times 10⁻31 kilograms. That's good. We didn't have to change any units. I could cancel with the kilograms in Planck's constant. And now our units match also for our velocity. 1 times 10⁶ meters per second. And so here we know that the seconds can cancel, and our kilograms can cancel, and then this 1 meters cancels with that one, and we're left with just one of those meters, right? So that's perfect. That's our wavelength. So then when we do this calculation, 7.27 times 10⁻10 meters is going to be the wavelength for that electron at 1 times 10⁶ meters per second. So again, with this portion, they found that electrons or matter, so de Broglie, he had that idea that matter could have wave-like behavior, and he proved that through experimentation with diffraction, and then he came up with the de Broglie formula, or the de Broglie relationship. Okay, on to the Heisenberg's uncertainty principle.